All right, let's dive right into this explainer because today we are exploring a really profound dichotomy in modern software. We're looking at two radically different approaches to how code interacts with the environment around it. On one hand, you have code that aggressively reaches out. It wants to connect, discover, and map everything it can. But on the exact opposite end of the spectrum, you have code that completely locks down. It absolutely rejects the outside world to maintain total internal purity. It's a fascinating contrast in architectural philosophy. So think about the fundamental nature of a script when you write it. What is its actual purpose? Is it a scout that you're sending out to actively traverse and map out the unknown digital world? Or is it a sovereign isolated vault designed specifically to keep the outside world out entirely? Really, every single line of code you write leans toward one of these two extremes, total exposure or absolute containment. Today, we are going to compare these two philosophies side by side. We'll look at the boundless, outward-reaching capabilities of a custom Python network scanner, and we're going to contrast that directly against the strict air-gapped and, frankly, kind of esoteric containment of a system called the FractalFJewel. Both of these are built in Python, yet they represent absolute polar opposites of computing. Act 1. Outward bound. Okay, let's look at this custom network scanner first. It is elegantly designed to probe subnets cleanly and efficiently, operating in 4 distinct steps. First, it defines a really strict timeout, say 0.8 seconds, so it doesn't get hung up waiting on dead IP addresses. Second, it runs a quick check, knocking on common ports like 22 for SSH, 80 for HTTP, and 443 for HTTPS, using Python's socket.connectX method. Third, it heavily utilizes threaded execution to scan a target subnet all at once. And finally, it safely uses a threading lock to compile a definitive list of responsive endpoints. You see, it is actively and enthusiastically engaging with the external environment. And this number brilliantly illustrates its speed, 50. The scanner is actually configured with a max threads parameter to fire off up to 50 concurrent workers at the exact same time. Just imagine 50 distinct digital scouts running in parallel, instantly checking standard ports across an entire IP range, just waiting to see who is home. It's highly efficient and, by design, purposely aggressive in its outward reach. The whole point of this Explorer program is to map local subnets like 192.168.1.0/24, acting as this energetic outward scout. It uses the ipaddress.ipnetwork module to easily parse that subnet into individual hosts, and it actively alerts you the very moment a live node is detected. It completely thrives on connectivity. It literally needs the network to function. Act 2. Inward bound. All right, let's shift gears abruptly. What happens when you build a program that views connectivity as a total liability? Enter the FractalFJewel. This is derived from an integrated source scroll documented in a massive PDF. The package combines a Python code tree, a C99 kernel, and inline emoji logging all into one unified, absolutely isolated fortress. It doesn't want to map your network. In fact, it doesn't even want to touch your hard drive. Its runtime contract is absolute. And wow, is it strict. It explicitly demands 0 network actions. No sockets, no HTTP, no SSH whatsoever. It refuses outward proliferation entirely, and it outright refuses to output a single runtime file. It is the exact antithesis of our network scanner. Where the scanner used sockets to reach out into the world, the Jewel explicitly outlaws them. This is an entirely self-contained, standard output-only environment. Actually, it is so paranoid about leaving a footprint that it's intentionally run with a command flag to block Python bytecode from caching to the disk. That means absolutely no -py cache left behind. It exists purely in memory and in the text scrolling on your terminal, guaranteeing total environmental purity. The FractalJewel core. So you're probably wondering, if a program flat-out refuses to write files or connect to a network, how in the world does it communicate its complex internal state? Well, it relies entirely on a terminal emoji spine to log its esoteric operations. Instead of writing heavy, bloated log files to a disk, it prints specific emojis directly to standard output. A blue gem represents the Jewel state, and a green dragon represents a specific mathematical operation known as the permute dragon. These visual markers allow a human to instantly audit the runtime flow without the program ever touching the hard drive. And as we look a bit deeper, we see more of these ancient-feeling visual markers popping up in the terminal logging. The blue diamond, for instance, tracks mathematically intense, bitwise operations called HEXPHIBIN folds. Or this pink worm emoji, which logs an esoteric module titled Worm Body Rhetoric. It essentially transforms what would normally be thousands of lines of boring text logs into a highly visual, completely ephemeral testimony. Because it is a fortress, its structural integrity has to be mathematically guaranteed. This closed-loop system is incredibly precise. Each of these esoteric files is locked to an exact byte size and a specific SHA-256 hash prefix. Take HEXPHIBIN pi, for example. It must be exactly 1011 bytes. If even a single space is added by some outside force, the hash prefix immediately breaks and the system instantly knows it's been tampered with. It mathematically guarantees it hasn't been compromised. This snippet here perfectly illustrates that internal logic. It shows how the program strictly manages bitwise operations, using binary ANDs and XOR deltas to verify vertices inside its completely air-gapped memory space. It is validating complex constraints and topological edges entirely in memory. It requires absolutely zero external dependencies. It trusts nothing but its own internal mathematics. Act 3. Exploration versus containment. Let's bring this all together. But first, I have to point this out because it's just a fantastic little detail. Despite the Jewels' ultra-serious, mathematically pure containment, the source material injects a great moment of levity. It notes that the entire source code is compiled into a single PDF scroll, remarking, "Humans demanded scrolls, then invented printers." I love that, because even in the most isolated, rigid systems, there's always a human element, a need for us to eventually read and comprehend the output. This juxtaposition really perfectly frames our tech reality today. On one side, you have the scanner using socket.connectxo to physically knock on network doors, bravely traversing the chaotic, untrusted web. But on the other side, the Jewel acts as a sovereign kernel, banning even the writing of a single tiny text file to disk just to prevent any possible injection or data leakage. So what does this all mean? The crucial takeaway is that we actually need both. We desperately need the energetic outward scanner to map our vast, messy networks and figure out where we're exposed. But we also need the heavy, isolated inward kernel of the Jewel to guarantee a pure, uncompromised safe room where our most critical logic can execute without fear of the very network that the scanner is out there traversing. While the network scanner is out traversing the external boundary, the Jewel relies on an internal compass, yielding a perfectly contained, memory-only C99 lawful commit. Notice the green checkmark there. That indicates the memory-only constraints held up perfectly. The operation was a total success, and not a single artifact was left behind to prove it happened, other than the terminal output you witnessed. Which leaves us with this final, fascinating question to take away. As our networking tools grow infinitely outward, constantly scanning and constantly connecting, does true digital safety require a return to absolute, sealed container? It's definitely something to chew on the next time you sit down to write a script. Are you building a window to the world, or are you building a safe? Thank you so much for exploring this with me today.
Welcome to this deep dive. If you are listening to this on a smartphone right now, or I don't know, maybe streaming it through a browser on your laptop, your device is just silently performing 1,000 little chores behind your back.
Oh, yeah, absolutely. Constantly.
Right. Like, just to buffer this audio, it has probably written a dozen temporary cache files. It's updating system registries. It's logging connection speeds. It is probably sending these tiny telemetry pings to a server halfway across the world just to say, like, hey, I'm still awake. I'm still connected.
Yeah, that pinging home behavior is just, it's baked into everything now.
Exactly. Modern software is heavy. It's inherently sticky. I always say it leaves muddy footprints all over your hard drive. But I want you to imagine, just for a moment, a piece of software that behaves exactly like a ghost.
A ghost in the machine, right?
Yeah.
But in a very literal architectural sense here.
Yes, a literal ghost. So this software performs these incredibly complex mathematical gymnastics, and it physically grounds itself by, like, probing the actual physical battery level of your laptop. It logs its entire thought process using this ancient-feeling stream of emoji hieroglyphs that just scroll down a black screen.
Which is such a wild visual.
It really is. And then the very millisecond its computations are complete, it just vanishes. The lights go out. And it leaves absolutely zero trace on your hard drive. I mean, no hidden caches, no error logs, no registry keys, nothing. It is as if it was never there.
Which is a massive subversion of, well, basically everything we are taught about modern software development.
All right.
We live in an ecosystem of persistent data. Applications are fundamentally designed to embed themselves into your operating system. What we are unpacking today is a software architecture that explicitly, philosophically, and mechanically refuses to participate in that reality. Like, it's a piece of code engineered to exist solely in the ephemeral moment of its own execution.
And the source material we have for our mission today is, honestly, every bit as fascinating as that core philosophy. We are opening up this highly unusual document, and it's simply titled Full Entire Integrated.pdf.
Yeah, quite a name.
Right. And it contains a complete, beautifully refactored code base. And reading through it, I mean, it feels less like reading standard software documentation and way more like discovering a forgotten grimoire or something.
It really does have that mystical vibe.
It outlines something called a Python code tree. It houses a mathematical engine that the developer refers to as a FractalFJewel C99 core.
And we can't forget the module names.
Oh man, the module names are incredible. You have individual modules with names like Bermuda Dragon and Worm Body Rhetoric.
Yeah, those names definitely suggest a developer who views programming as an almost like esoteric practice rather than just mundane engineering.
I was half expecting to find instructions for drawing chalk circles around the server rack, honestly. But our goal here is to cut through all that mystique. We're going to unpack the strict mechanics of this completely hermetically sealed digital environment. We are going to figure out why someone would build a hyper-complex mathematical system complete with jewels and dragons that intentionally disables all network access and completely refuses to write a single output file.
To understand the why, though, we have to rigorously examine the how. And that begins with the foundational laws of this ecosystem, which the developer has actually codified into a runtime contract.
Yeah, let's open up that contract. So inside the source document, there are two specific text files that lay down the absolute law of the land. They are noRuntimeFileOutput.md and safetynotes.md. And the prohibitions listed in here are just uncompromising.
Completely draconian.
Literally. There is no runtime file writing permitted whatsoever. No log files to track progress. No report files to export data, no network scanning, no sockets, no HTTP or SSH activity to talk to the outside world, no deployment mechanisms, and absolutely no replication. It is a digital hermit kingdom.
The terminology we use in computer science for this is a complete embargo on side effects.
Let's pause there for a second because that term gets thrown around a lot. For anyone who isn't, actively writing compilers or debugging state machines, what exactly constitutes a side effect in the context of software?
Okay, so a side effect is anything a function or a piece of code does that interacts with the outside world beyond simply returning a mathematical value to whatever called it.
Okay.
So if I ask a function to add 2 plus 2, the expected return value is 4. If, while calculating 4, that function also turns on your webcam or writes a line to a text file on your desktop saying I calculated 4, or pings a time server in Geneva, those are side effects. The function altered a state outside of its own localized environment.
It disturbed the universe.
In a micro sense, yes. And this architecture enforces a zero side effect policy. And it goes to extreme, almost hostile lengths to guarantee that the universe remains undisturbed.
Right, which is so weird because to contextualize just how strict this is, I want to bring up another piece of code that was actually included in the source dump. It's this Python script called Sovereign Network Discovery Module.
Ah, yeah, the network scanner. That is a perfect point of contrast.
It really is. It's built using the standard Python socket and threading libraries, plus the IPaddress module. Basically, it defines this network scanner class, and it takes a subnet like 192.168.1.024, and it spins up to 50 concurrent threads to scan for live hosts.
Yeah, and it specifically checks common ports, right? Like port 22 for SSH, 80 for HTTP, 443 for HTTPS.
Exactly. It uses a quick socket connection with a 0.5-second timeout to see if those ports are open. And if they are, it prints out a little check mark and the IP address. It even prints a warning saying only use on networks you own or control.
Which is standard cybersecurity hygiene for a scanner, sure.
Yeah. But the reason I bring this Sovereign Network Discovery module up is because it is the exact opposite of what the FractalFJewel system allows.
Oh, 100%.
Yeah.
That scanner is loud. It's probing external IP addresses. It's opening sockets. It's firing off dozens of threads to touch things outside of itself. It is pure side effect.
Right?
And the creator included it in the materials, I think, to explicitly show the kind of conventional, noisy software behavior that the core Hermit Kingdom system violently rejects. The core system would rather die than import a socket library.
It's just a totally different paradigm. And it goes even further than just banning external network pings. Consider how the Python programming language operates by default on your local machine.
Right, it tries to be helpful.
Exactly. Python usually tries to be incredibly helpful. Like if you write a Python script and hit run, Python knows that translating your human-readable text into machine instructions takes time. So in the background, it quietly compiles your code into bytecode and drops it into a hidden folder called _pycache _.
Yep, the PyCache folder.
Or it saves it as .p files. The idea is that the next time you run the script, Python can just read the pre-chewed bytecode and launch much faster. It's just an automatic built-in optimization.
An optimization that this specific developer views as a literal contamination of the environment.
Yes.
They force the user to bypass that helpfulness completely. The documentation explicitly mandates that the Python environment must be launched from the terminal with a very specific, aggressive command. It's python.write bytecode equals 1 space python 3 space -b space demo.py.
That -b flag and the environment variable are essentially a muzzle on the Python interpreter. It is telling the language itself, do not, under any circumstances, drop your little performance crumbs on my hard drive.
Right, leave no trace.
Yeah, like I don't care if it makes the next run slower. Leave no footprint.
The system is deliberately overriding the programming language's own fundamental behaviors to ensure that the before and after state of the hard drive remains entirely unchanged. In their verification snapshot, they actually proudly record the result, writing, Python demo ran with before-after file list unchanged.
Okay, here is where I have to step in and play devil's advocate for a minute,
Yeah.
because the sheer isolation of this is staggering. Looking at this architecture, it reminds me of a Vegas magic show.
Okay, I like that. How so?
Think about it. You are sitting in the audience. There is this massive flurry of activity on stage. Lasers, smoke, things vanishing into thin air and reappearing across the room. It takes immense coordination and energy. But the moment the curtain drops and the house lights come up, the stage is completely empty. There is zero physical evidence that any of that magic actually happened. So my question to you is, what is the actual practical point of a program that doesn't save anything and refuses to communicate? It's like a chef spending 10 hours cooking a massive, complex, 5-course Michelin star meal, plating it perfectly, and then throwing the entire thing straight into the incinerator before anyone takes a single bite.
That Vegas stage metaphor is actually perfect for understanding the developer's mindset. But let's stick with the chef throwing the meal in the incinerator for a second.
Okay.
When you do that, you don't get to eat the food, true. But you still fundamentally prove that the recipe works. You prove that the ingredients combine in exactly the chemical way you hypothesized.
But the whole point of software is usually to produce a result we can keep. I mean, we want the meal.
Usually, yes.
Yeah.
But in this specific architectural philosophy, the meal isn't a file you save for later. The meal is the absolute unassailable truth of the process itself.
The truth of the process.
Yeah. By stripping away all side effects, by brutally severing the ability to write to a disk, query a network like that scanner script does, or accept an outside ping system, the developer guarantees that the system's state transitions are entirely purely self-contained.
Meaning nothing from the outside can ruin the recipe while it's cooking.
Exactly. There is no external variable that can corrupt the math. An interrupted Wi-Fi connection can't crash it halfway through. A sudden lack of hard drive space can't corrupt a save file. A rogue background process can't inject malicious data. It is a closed-loop ecosystem designed for perfect auditing.
So the goal isn't utility in the traditional sense at all. The goal is control, like absolute paranoid control over a digital terrarium.
Control and perfect predictability. If the system can only act upon itself and its internal rules are mathematically rigid, then every single execution is perfectly deterministic.
Right.
If you run it 1 billion times, you will get the exact same sequence of events 1 billion times. The value isn't in what it produces to the outside world. The value is in the flawless execution of its internal logic.
I can appreciate the beauty of a perfectly sealed terrarium. I really can. But if this system is trapped inside glass and it absolutely refuses to write a single log file to tell us what it's doing, how do we know what's actually happening inside the incinerator?
That is the big question.
Right. How do we watch the magic show? If everything is banned, how does it communicate its success or failure? Which brings us to one of the most visually wild parts of this entire document, which is the terminal output.
Since traditional text logs are banned by the runtime contract, the software routes all of its operational testimony to standard output, which is just the live terminal screen using what the developer calls a terminal emoji spine.
Yeah, when I first opened terminal_emoji.py, I honestly thought it was a joke. I want you, the listener, to visualize the dashboard of an alien spacecraft. Usually a developer watching a live server log is staring at boring, dense lines of text scrolling down a black screen. It's stuff like error 404 at timestamp X or process thread 7 initialized.
Very dry stuff.
Super dry. But this developer is watching an incredibly vibrant psychedelic stream of dragons, jewels, and stop signs scrolling down the terminal.
The visual language they have mapped out in the code is highly specific, though, and strictly categorized. Every core function has a designated glyph.
Let's walk through some of them because they're great.
Sure, so when the system performs an internal audit, it outputs a scroll.
Like an ancient parchment emoji.
Yeah, exactly. When it checks its own territorial boundaries, it prints a compass emoji. When it probes the physical power supply of the host machine, it drops a battery symbol. The state of the core mathematical nodes that the system calls its jewels are represented by, appropriately, a diamond jewel emoji.
And then it just gets delightfully esoteric. We have a stopwatch emoji for something called a tick, which validates a change. We have a blue diamond for a HEXPHIBIN fixed point fold, a green dragon for the Bermuda dragon function.
The dragon is a nice touch.
It is. And there's a hash key for when it hashes its own data with SHA-256, a literal pink worm emoji representing the worm body rhetoric module, and an evil eye talisman representing the C99 clone of the code.
Crucially, it also uses emojis for the binary outcomes of operations.
Right.
A lawful, mathematically valid commit is a bright green checkmark. A refusal, or a failed constraint check, is a red octagon, a stop sign.
Looking at this list, my first instinct is that it almost feels like I'm looking at a heart monitor instead of a text log. Is that the point here? To bypass the reading part of the brain and tap into something more instinctual.
You've hit on the exact cognitive benefit of this design, actually. Think about how human beings process information under load. In a fast-moving terminal window where lines of diagnostic output are scrolling by at hundreds of lines per second, the human eye is remarkably terrible at parsing dense walls of text.
Oh, it's impossible.
Right. If the word error is buried in the middle of a paragraph of gray ASCII characters, you will absolutely miss it.
It just becomes that classic matrix code waterfall. It washes right over you.
Exactly. But our visual processing cortex is incredibly highly tuned for pattern recognition and color disruption. We evolved to spot a bright red berry in a bush of green leaves. If you have a terminal rapidly scrolling with green checkmarks, blue diamonds, and pink worms, your brain establishes a visual rhythm.
It literally becomes a heartbeat.
Yes. You don't read it, you absorb the cadence.
And if something goes mathematically wrong inside the terrarium?
If a single red stop sign or refusal breaks that visual rhythm, your eye catches the color disruption instantly, even if the text is scrolling at light speed. The developer doesn't have to painstakingly read a postmortem text file to know the system is healthy. They can physically feel the health of the system based on the color and shape of the scroll in real time.
Wow.
It transforms logging from a tedious forensic chore into a live diagnostic pulse.
You're not reading a manual, you're watching a patient's vitals. It is brilliant. But looking closely at the specific emojis, especially the compass and the battery, it reveals a really fascinating tension in the source material.
What do you mean?
Well, we have this system that is supposedly totally isolated. It's mathematically pure. It speaks only in pictograms. It refuses to touch the network or the hard drive. It feels incredibly ethereal. But if we follow that compass emoji into the boundary search territory package, we discover that this isolated ghost is actually hyper-aware of the physical world. It has an almost paranoid relationship with the hardware it lives on.
Ah, yes. The isolation of this software is not a product of ignorance. It is an enforced, heavily militarized boundary, and the system patrols that boundary aggressively. We see this detailed in two very revealing files, boundary.py and batterystats.py.
Let's start with boundary.py. If it's so intent on never recording its state, what happens when it's forced to look at the hard drive just to verify its own existence?
Yeah, it imposes strict limits.
Yeah, the code is allowed to search its own local directories to audit itself, but the constraints it puts on itself are staggering. It caps its own directory searches at exactly 256 files. If it hits file number 257, it drops a hard stop. It explicitly skips any file larger than 1 megabyte. And most notably, it violently refuses to follow symlinks.
The limitation of 256 files is a classic computer science threshold 2 to the 8th power, a clean byte of data. It represents a strict cap on memory and computational time dedicated to a non-core task.
And the 1 megabyte limit.
That's a defense against memory exhaustion. If a malicious actor places a 50-gigabyte dummy file in the directory, a naive program might try to read the whole thing into memory to audit it, and that would cause the system to crash. By ignoring anything over a megabyte, the program guarantees it can never be suffocated by its environment.
That makes sense.
But the symlink prohibition is where the true paranoia lies. For those who might not spend their days in Linux environments, a symlink or symbolic link is essentially a shortcut file. It points to a file or a folder located somewhere else entirely on the file system.
I always picture it like a bank vault that gives the security guard a map. The map says, check room A, check room B. But a symlink is like a fake door painted on the wall of room B that actually drops the guard out the back of the bank and into the manager's private office.
That is exactly how symlink attacks work in cybersecurity.
Oh, really?
Yeah, if a program blindly follows a symbolic link while doing a routine scan, a malicious actor could use that link to trick the program into reading highly sensitive files far outside of its intended safe directory, like a root password file or user credentials located deep in the operating system.
So the ghost could accidentally read the host's diary.
Right. And by explicitly checking for and refusing to follow symlinks, the Boundary Search Territory module acts as a relentless border patrol. It mathematically ensures the software can never be tricked into escaping its designated quarantine. If a path tries to resolve outside the allowed root directory, it throws a literal value error that reads, path escapes boundary search territory.
It trusts absolutely nothing. It is constantly checking over its digital shoulder. Which brings me to what I consider the absolute most bizarre module in this entire code base, batterystats.py.
Yeah, this one's unique.
This deeply isolated, theoretical, mathematical construct actively reaches out to probe the physical computer's power state.
It does. The script attempts to use the Python pseudo library if it happens to be installed. If it's not, software doesn't just give up. It falls back to reading the raw Linux CIFS power supply files.
Wait, what does that mean?
So in Linux, everything is treated as a file, including hardware sensors. So this ghost is literally checking /sys/class/power_supply on the hard drive to read the physical voltage.
It's checking if the laptop is plugged into the wall. It determines if the system is on wall power or low power, meaning under 20% battery, balanced meaning under 50%, or portable high. So here's my big question for you.
Okay, lay it on me.
If this code is so obsessed with being a pure, isolated, floating mathematical construct that leaves no trace, why on earth does it care if my Lenovo ThinkPad is plugged into the wall? Why does a mathematical ghost have battery anxiety?
Because it recognizes a fundamental, inescapable truth that an alarming number of modern software developers completely ignore.
Right.
Software does not run in a void.
Right.
It is not purely ethereal. Software consumes physical electrons. The execution of a mathematical formula creates physical heat inside a silicon processor. What we are looking at here is an architecture that we might call physic-aware.
Physic-aware, that is a great term. It knows it has a body.
Exactly. It acknowledges the host organism. If you are running a highly intensive mathematical cascade, which is what this codebase calls its calculation loops on a laptop, and that laptop is starving for power, say under 20% battery, a truly elegant system shouldn't just blindly drain the last of the lifeblood to compute its own internal logic.
It's like a parasite realizing the host organism is dying and deciding to slow its own metabolism down so they both survive the night.
Precisely. By monitoring the physical battery, the system roots its theoretical zero-footprint math firmly into physical reality. It bridges the gap between the abstract algorithmic thought and the physical electrons required to manifest that thought.
Wow.
Now, while the code we have doesn't explicitly rewrite its math based on the battery, the framework is there to theoretically throttle its computational intensity, its cascade based on available power.
It's remarkably polite. Like, the ghost doesn't want to spin up your laptop fans and run up your electric bill. But this all raises the central question. We've talked about how it refuses to leave logs. We've talked about how it speaks in emojis. We've seen how it paranoidly checks its boundaries and its battery life. But what on earth is it calculating that requires this level of isolation and physical caution? Let's open up the actual mathematical engine of this beast.
Right. The brain of the entire operation resides in two heavily complex files, HEXPHIBIN.py and JewelModel.py. This is the mathematical core they refer to as the FractalFJewel and the FreeKernel.
I opened HEXPHIBIN.py, and frankly, it looks like alien algebra to me.
It is definitely dense.
It is heavily utilizing something called 16-bit shift operations. There's a constant defined as Q16 shift equals 16, and it's running a massive amount of fixed point math that revolves entirely around the golden ratio. It literally defines constants for the golden ratio PHI, PHINV, PHI2, and PHI3.
Let's unpack the golden ratio first because it dictates the structure of everything else.
Yeah, please do.
PHI, roughly 1.618, is a famous mathematical constant. It appears constantly in the natural world, from the spiral arms of galaxies down to the arrangement of leaves on a plant stem or the curve of a nautilus shell. It possesses unique, incredibly elegant mathematical properties regarding scale, symmetry, and recursion.
Right, if you take a golden rectangle and cut off a square, you are left with another smaller golden rectangle, and it just goes on forever.
Precisely. It is inherently fractal. By building a mathematical fold based on the golden ratio, the system is likely generating deterministic fractal-like state changes. It takes a numerical value and folds it together with phi and its inverses to create a new, mathematically distinct state that is topologically related to the previous state.
But if I open up the calculator app on my phone and do math with the golden ratio, I'm just typing in decimals. 1.61803. Why is this ghost using 16-bit shift operations and fixed point math? Why can't it just use decimals like a normal program?
Because normal decimals, what computers call floating point math, are the absolute enemy of determinism.
Really? Why?
Floating point math is famously unpredictable across different hardware. An Intel processor and an ARM processor inside an iPhone might calculate the 50th decimal place of phi slightly differently due to how they handle microscopic rounding errors.
Oh, wow. And in a closed-loop terrarium where one altered bit means a red stop sign emoji, you just cannot tolerate a hardware-level rounding error.
You absolutely cannot. Fixed-point math solves this. Instead of dealing with floating decimals, you take a whole integer and you virtually declare that the last, say, 16 bits of that number represent the fraction. That's the bit shift.
Wait, pause for a second. For anyone who isn't writing a low-level compiler right now, physically, what is happening on the silicon when you say shift a bit 16 spaces?
Sure. Think of binary code in a computer's memory, like a long row of physical light switches.
Okay, light switches.
On is 1, off is 0. If I have the number 5 in binary, and I told the processor to shift it left by 1, the processor literally takes the physical sequence of switches and slides them all one slot to the left, adding a 0 at the end. It's an incredibly fast hardware-level operation. Sliding binary to the left by 1 multiplies the number by 2.
Okay.
Sliding it by 16 spaces multiplies by 65,536.
And it does this because sliding switches is infinitely faster and more reliable than asking the processor to do long division with decimals.
Yes, exactly. It is raw, bare metal math. It forces absolute integer precision. There's no rounding ambiguity whatsoever. By using 16-bit shifts and fixed-point math, the developer ensures that the golden ratio calculations will resolve identically down to the exact atomic bit, whether the code is running on a multi-million-dollar supercomputer or a 10-year-old Raspberry Pi.
It is absolute mathematical universality, and these perfectly precise numbers are held inside what the code calls joules. The joule model.py file defines a joule class, and each joule seems to be a node or a particle in this system, and it holds a state represented by what they call clean vertices, bits A, B, and C.
Think of a joule as a fundamental subatomic particle within the software's universe. It holds a specific state, represented by the configuration of those A, B, and C bits. And managing the collection and interaction of these joules is the entity known as the fine kernel. The kernel is the universe in which these particles exist.
And the way these particles interact is through a mechanism called a tick. The system undergoes a tick where it receives proposed changes to the joules. It calls these proposed changes deltas. The analogy that instantly sprang to my mind when I was reading through the kernel validation code was a nightclub bouncer, or maybe an impossibly strict IRS auditor.
A bouncer to the universe.
Yeah.
Okay, how so?
Well, imagine the joules lining up at the door. They submit their proposed changes, their deltas, their tax returns, whatever, to the kernel. The kernel takes these deltas and runs them through that incredibly fast golden ratio math shredder we just talked about, but it doesn't just blindly accept the result. It rigorously validates the changes against an unbelievably strict set of constraints. The code lists them out as match, mismatch, XOR, and bridge.
The bridge constraint is particularly fascinating because it uses a Hamming 3 distance calculation.
Hamming distance, is that like physical distance?
It is topological distance. In information theory, Hamming distance, named after Richard Hamming, who developed it at Bell Labs in the 1950s, is a metric for comparing two strings of data. Specifically, it counts the exact number of positions at which the corresponding symbols or bits are different.
So if I have a string of 5 zeros and a string of 4 zeros and a 1, the Hamming distance is just 1 because only one bit flipped.
Exactly. It measures the minimum number of substitutions required to change one state into the other. So when the FractalFJewel applies the bridge constraint using Hamming 3, it is mathematically verifying the exact topological distance between two proposed Joule states. It wants to know exactly how many bits are flipping before it allows those states to connect or alter.
It wants to know the exact geometric shape of the change.
Yes.
And if even a single bit is out of place, if the Hamming distance calculation is wrong by one integer, or if the MATCH requirement fails, the strict bouncer at the door flashes that red stop sign emoji.
The refusal.
Exactly. It throws a rigid value error, something like unknown constraint kind, or illegal delta refused, and it denies the change completely. The system state does not advance. Only if every single mathematical proof holds up to scrutiny does the kernel emit a green check mark. A lawful commit.
Which highlights the absolute beauty and rarity of this deterministic state machine. In modern commercial software development, it is incredibly common for a program to enter a partially corrupt state.
Oh, all the time.
Maybe a network call failed halfway through a download, or a file was only partially written to the disk before the battery died, and the software just limps along. It throws invisible errors, it acts sluggish, until it eventually reaches a fatal contradiction and crashes.
Yeah, we've all experienced the classic, like the application is completely frozen, but I can still move the mouse cursor situation. It's just half dead.
But inside the FractalFJewel, it is mathematically impossible for the system to enter an undefined, half-dead, or corrupt state. Every single proposed change is submitted as an isolated delta. That delta is mathematically projected forward into a hypothetical future state. The topological edges, those A, B, and C bits, are cross-examined against the strict Hamming constraints. And only when the entire equation balances perfectly in the hypothetical is the actual system state updated. Wow. If it fails, the state remains exactly, pristinely as it was before the tick. It is a transactional, bulletproof design.
It is architecture as mathematical proof. It doesn't assume it works. It forces the math to prove it works before taking a single step, which makes it incredibly robust. But here is where the developers did something that really, truly blew my mind.
The C clone.
Yes. Python is a fantastic language for prototyping this kind of logic. It's readable, it handles the emojis beautifully, it allows for fast iteration. But they didn't stop with Python. They built a parallel universe.
It did. Tucked away inside the boundary search territory folder is a directory labeled Fractal C99.
They completely rewrote the exact same FractalFJewel kernel, the entire bouncer logic, in C. We have a FractalFJewel.c file and a demo.c file. Why write the same incredibly complex mathematical poem twice in two different languages?
To understand why, you have to understand the fundamental difference between Python and C99. Python is a high-level interpreted language. It is designed to be friendly. Think of Python like having a really smart, coactive assistant who handles all the messy physical details for you.
Okay.
If you want a list of data, you ask Python for a list. Python goes to the computer's RAM, finds the necessary memory, builds the list, and crucially, when you are done with it, a background process called the garbage collector comes by and sweeps up the memory so it can be reused.
You never have to think about the physical hardware. You just write the logic.
Right. C99 is the antithesis of that.
Yeah.
The C99 standard was finalized in 1999, and it operates incredibly close to the bare metal of the processor. It has no assistant. It has no garbage collector.
Oh, wow.
If you want memory in C99, you have to negotiate with the operating system yourself. You manually allocate the bytes, you use them, and if you forget to manually free them when you are done, the system's memory leaks and crashes. It is dangerous, it is manual, but it is pure, unadulterated control. Code written in C99 30 years ago will likely still compile and run perfectly 50 years from now. It is timeless.
But implementing this hermit kingdom in C requires a fundamental compromise to their most sacred rule, doesn't it? Their rule is no files.
It does.
But there is a brilliant piece of commentary in the developer's readme.md about this exact contradiction. It says, the make step creates the demo binary because compilers are needy little factories. The program itself prints only to terminal.
Needy little factories. It is a wonderfully self-aware phrase.
I honestly laughed out loud when I read that, because it perfectly captures the irony they found themselves in. This entire system is ideologically violently opposed to creating files on the hard drive. But C is a compiled language. You can't just run the raw text file like you can with Python. You have to let the C compiler crunch the text code and spit out a physical compiled binary executable file onto the hard drive like demati99.exe just so the computer's processor can read it. It is a necessary physical evil just to exist in the C universe.
It is a necessary physical artifact. But notice how carefully they justify it. The compiler is the factory. It builds the machine. But once the binary is built and running, it rigidly adheres to the exact same runtime contract. The verification snapshot provided for the C version explicitly shows the terminal output reading C99 demo compiled and returned, OK equals 1, commit equals 1, edges equals 3, runtime file output equals 0.
So it still doesn't write anything.
Exactly. Even though it had to be born as a file, the running process still leaves no trace during its own execution.
So why go through the headache? Why build this beautifully strict, isolated bouncer in Python, perfectly balanced, and then subject yourself to the manual memory management and needy little factories of C99?
To mathematically prove the universality of the logic. By proving that the exact same deterministic, side-effect-free architecture works identically in a high-level, garbage-collected language like Python, and in a bare-metal, manually managed language like C99, the developer elevates the concept. It is no longer just a neat Python script. It proves that the jewels fold with the golden ratio and the Hamming constraints hold, regardless of the environment they are placed in. It proves it is a universal mathematical truth.
The logic entirely transcends the language it happens to be spoken in.
Exactly. And the terminal verification confirms it perfectly. You run the Python demo, and there is a zero-line diff in the file list before and after. You compile and run the bare metal C99 demo, and you get runtime file output equals 0. The Ghost behaves exactly the same way, whether it's wearing a modern Python sheet or a 1999 bare metal sheet.
Okay, let's zoom out and unpack this whole journey, because we have covered a massive amount of conceptual ground today. We started by looking at a software system built on an absolute paranoid zero-footprint philosophy, the no-trace contract that violently refuses to leave logs, caches, or network pings on the host machine.
Right. And we examined how it bypasses traditional logging, routing its operational heartbeat purely visually. It uses a highly specific terminal emoji spine that leverages human visual processing and pattern recognition over tedious text parsing.
We looked at its territorial boundaries, watching it actively refuse to follow symlinks to prevent escapes, while simultaneously grounding its ethereal, floating math in physical reality by reading the sys-class power supply to monitor the host computer's battery electrons.
And finally, we descended into the mathematical core itself, the FractalFJewel and the Phi kernel. A deterministic, golden ratio-driven state machine utilizing fixed-point bit shifts. A system that uses Hamming distances to rigorously validate the exact topological shape of every single change before allowing a lawful commit, proving its universality across both interpreted Python and bare metal C99.
It is a breathtakingly tight, disciplined piece of engineering, and I think the real value of this deep dive for you, the listener, is how sharply this entire document contrasts with the digital water we are all swimming in right now. It fundamentally challenges the modern assumption that software must be sprawling. It challenges the idea that it must constantly phone home to a server, that it has to leave endless logs, telemetry data, and registry keys scattered across our hard drives just to justify its existence.
It proves mathematically that complexity does not require sprawl. You can have highly complex, rigorously validated, conceptually massive operations contained entirely within a closed ephemeral loop.
Which leaves us with a final, somewhat provocative thought to mull over as you close out of whatever app you are listening to right now. We live in an era heavily characterized by data harvesting. Invasive telemetry is baked into the DNA of almost every tool we use. Our applications are bloated, sticky, and desperately dependent on cloud connectivity. Given all of that, could the radical ephemeral computing demonstrated by the FractalFJewel software that exists solely in the moment of its execution, proves its own mathematical truth, and then vanishes like a ghost, leaving absolutely zero trace behind on your drive or on the network, could that isolated hermit kingdom approach be the ultimate frontier for digital privacy and security?
If a system leaves nothing behind, there is no history to exploit.
The ghost leaves no footprints to follow. Thanks for taking the deep dive with us.
Welcome to This Explainer. Today, we're unpacking something completely wild. It's a highly unusual, deeply esoteric software artifact known as the FractalFJewel codebase. You know, if you're used to those massive, sprawling cloud architectures, endless dependencies, and microservices that just span dozens of servers, you are going to find this incredibly fascinating. We're essentially looking at a piece of code that acts as an absolute minimalist digital hermit.
Okay, let's jump right in. Because this source material, it isn't just software. It actually views itself as a single, unified scroll that totally rejects modern software sprawl. The creators deliberately compiled everything into one source-only integrated zip, and they presented it as a PDF document. So right out of the gate, it's a massive philosophical statement. They even joke that humans demanded scrolls and then went and invented printers. It really highlights this desire to return to a continuous, unbroken sequence of information rather than dealing with scattered, fragmented files everywhere.
What we're looking at here is a totally self-contained ecosystem. It integrates a Python code tree, a C99 kernel, and this highly unique mechanism they call emoji terminal logging. As you can see, this whole thing is about running an incredibly complex mathematical boundary search, but doing it without leaving a single footprint. It is entirely ephemeral. It exists, it computes, and it vanishes.
To really wrap our heads around this artifact, we first have to understand its incredibly strict runtime contract. Now, every piece of software has things it's built to do, right? But FractalFJewel is defined entirely by what it refuses to do. It's allowed to read its bounded local source files. It can print emoji log lines to the standard output, and it can compile its C99 demo. And that is literally it. The list of what's been removed or neutralized, well, that's where the real story is.
So the absolutely crucial point here is that this software is strictly forbidden from doing almost everything modern apps do. There is zero network scanning, no pinging subnets to check if hosts are up, no HTTP requests, no SSH. It doesn't create log files, it doesn't drop report files, it doesn't even write a bytecode cache. In a world where practically every script seems to reach out to the internet or write temporary files to your hard drive, this artifact remains completely isolated, completely sovereign.
Now, you might be wondering, if it doesn't write logs, how do we know what it's doing? Well, take a look at the emoji terminal's spine. Since the program leaves absolutely no report files behind, these emojis printed directly to your standard output, your terminal screen, are its only runtime testimony. It uses very specific symbols to tell you exactly what it's doing in memory. For instance, whenever the program accesses memory or checks its topology, it communicates by emitting these visual symbols right to the terminal. The little scroll emoji? That represents an audit. It's copying arrays in memory. The compass emoji represents a boundary, adding or verifying a topology edge. Honestly, it's like watching a translated story unfold in real time. It's completely visual and entirely contained within that terminal window. At the absolute core of this whole system is the Jewel state, which is represented by that diamond emoji. This acts as the mathematical and memory anchor for the entire execution. Pretty much everything the program does is about adding these jewels into an in-memory kernel, validating their states, and then checking the boundaries between them. Looking closely at the Python architecture handling all this, we find an array of frankly fascinatingly named modules that make up this boundary search territory. You've got your standard functional files like boundary.py and jewel_model.py. But then you have these highly esoteric names, permute_dragon.py or worm_body_rhetoric.py. It really adds to the mystique of the artifact, blending strict mathematical topology with this almost mythical naming convention. This excerpt brilliantly illustrates how that jewel_model.py module rigorously validates states. The system takes a mathematical projection, checks if it's legally sound, and if it is, it applies a bitwise change, an XOR delta, before emitting its emoji ticks. It is just incredibly precise. All of this magic happens inside what they call the phi kernel tick. And the rules here, they are absolute. It verifies edges and calculates Hamming distances, which is essentially measuring the exact differences between vertices in memory. If literally any constraint fails during the tick, say a joule is missing or an illegal delta is attempted, the entire process just halts and emits a red refusal emoji. Every single thing must be perfectly mathematically sound for it to proceed to a lawful commit. Remember how I mentioned earlier that this program refuses to leave a footprint? Well, even the command to run the Python demo is hyper-restrictive. By enforcing the environment variable Python don't write bytecode equals 1 and using the -b flag, the creators ensure that absolutely zero compiled.pyc cache files are created on the host machine. The code runs, it exists purely in RAM, it prints to the screen, and then it vanishes. Now, all this logic feeds seamlessly into the C99 FractalJewel kernel. The Python code is really just one half of the artifact. The other half is a mirrored, highly optimized version of this exact same logic written in C99 and designated by the Nazar Amulet emoji. And yes, the C implementation adheres to the exact same hyper-strict runtime contract as the Python version.
We can actually trace the execution timeline just by reading the C99 terminal logs. It basically reads like a sequence of events. It starts with the seedling emoji for kernel initialization, moves to the diamond to add jewels in memory, the compass to establish topology edges, the stopwatch to begin the phi kernel tick for verification, and finally it ends with that green checkmark, the lawful commit.
And check out the actual terminal output proving this. When it finishes, it literally prints OK equals 1, commit equals 1, edges equals 3, runtime file output equals 0. Plus, if you run a before and after fileless difference check on the system, it shows exactly 0 lines changed. It's an entirely ephemeral, flawless execution that leaves the host machine exactly the way it found it.
Now, full disclosure, there is one tiny exception here, but the source material addresses it beautifully. I absolutely love this specific detail. They acknowledge that to run the C code, the C compiler intrinsically has to create a demo binary file. They justify this by stating, quote, compilers remain tiny industrialists. So the compiler may build a factory, but the FractalFJewel C99 program itself remains pure. Once it's running, it prints only to standard output.
So what does this all mean? It leaves us with a pretty fascinating final thought. We live in an era where software wants to connect to everything, log everything, and just sprawl across these massive cloud deployments. But by imposing ultimate restrictions on what our code can do, forcing it to exist solely in memory and speak only through visual symbols on a screen, do we actually unlock a purer form of digital art and logic? It's the kind of question that makes you look at the bloated software sitting on your computer right now in a completely different light.
Hey everyone, and welcome to this explainer. Today, we're unpacking an incredibly constrained, just totally esoteric programming architecture known as the FractalFJewel. Seriously, if you're used to modern software development, where applications sprawl all over file systems, they're constantly pinging servers, generating gigabytes of log files, what we are about to look at is going to feel like landing on another planet. We're diving into a completely self-contained, integrated codebase that fundamentally rejects the way almost all modern software operates. It's a really fascinating exercise in digital minimalism and just absolute systemic control. Okay, let's just dive right into this by establishing the extreme, completely unyielding rules that this system actually operates under. Listen to this. No runtime file writing, no log or report file creation, and it goes on to explicitly ban network sockets, HTTP, SSH, and literally any form of deployment or replication. This isn't just, a best practice guideline. No, it is a hard-coded, unbending physical law of the FractalFJewel environment, which immediately forces us to ask, if a program can't write a file, can't cache its data, and absolutely cannot reach out to a network, how in the world can we possibly know what it's doing, or even verify that it works at all? Well, here is our roadmap for figuring that out. We'll start with a strict runtime contract, then look at the terminal emoji spine, followed by jewels and boundaries, Python and C99 integration, and finally, execution and verification.
All right, Section 1, the strict runtime contract.
Now, what's really striking here is the massive contrast between the very few allowed actions and the huge list of banned capabilities. The system is permitted to read its own bounded local source files. It's allowed to print very specific emoji logs to standard output, basically your terminal screen, and it's allowed to compile a C99 demo via a makefile. And that is it. On the neutralized side, the restrictions are absolute. No file writing whatsoever. Even the standard Python bytecode cache, those temporary files your computer usually saves just to run scripts a bit faster, explicitly blocked using environmental variables. Network actions, completely neutralized. It is a 100% sovereign, closed-loop environment.
Moving right along to Section 2, the terminal emoji spine.
So instead of spitting out those massive, impossible-to-read walls of text for debug logs, this system emits highly structured, prefixed standard output using emojis. It's brilliant. The scroll icon represents an audit event. The compass denotes a boundary edge. The diamond, that represents a jewel's state. That little blue eye symbol shows us actions taken by the C99 kernel. And the green checkmark is the ultimate goal here, a lawful commit. By standardizing this inline emoji logging, the developers essentially created a visual spine. You can instantly read it as it streams down your terminal, guaranteeing transparency without ever having to touch the hard drive.
Next up, Section 3, jewels and boundaries. So, what is the actual data we're dealing with? Well, the fundamental unit of state managed by the system is known as the jewel. In the source material, the Joule is this highly structured class that tracks modes, vertices, and bit states. It's essentially a perfectly crystallized packet of data that has to adhere to really strict internal validation rules before it can even be processed. Whenever a Joule is initialized or when its state is verified, the terminal emits that diamond emoji to let us know, hey, a piece of core state is being handled right now. But of course, Joules don't exist in total isolation. They're connected by topology edges, which the system refers to as boundaries, represented by the compass emoji. Think of the Joules as nodes and the boundaries as the strict relational rules connecting them. The code base is just constantly validating these boundaries. It's checking, do the constraints hold between these two Joules? Are they a match? Is there a valid XOR relationship? If a constraint fails, even slightly, the boundary breaks and the entire operation is completely refused. It's this beautifully rigid topological network mapped entirely in memory.
Which brings us to Section 4, Python and C99 integration.
To actually pull this off, this dual nature setup uses a high-level Python script to sort of orchestrate the environment, right? And then it passes the heavy lifting down to a deeply constrained C99 execution kernel. So the Python side handles the overarching rules, the object models for the Joules, and it ensures that the runtime environment is perfectly sterile before doing anything. But when it comes time for the heavy, low-level execution, that logic is mirrored and processed by raw C99 code. It's kind of like Python is the strict architect setting the ground rules, and C99 is the focused builder executing the work in absolute silence. And remember that I symbol? That denotes the C99 kernel, which strictly adheres to that stat-out-only mandate. It runs entirely in memory without dropping a single file. Actually, the source text delightfully points out that the only exception to this is the compiler itself creating the demo binary, because, quote, compilers remain tiny industrialists. I love that phrasing. But the actual running C99 kernel, it operates like an absolute ghost. It initializes, copies dual arrays, verifies edges, and validates legal deltas entirely in RAM. It speaks to us only through that terminal emoji spine we talked about.
Finally, Section 5, execution and verification.
So let's look at how this plays out in real time. This sequence shows the exact rapid-fire logical flow the C99 kernel executes to process these Joules and verify those topology edges perfectly in memory. First, the seedling emoji pops out, indicating the kernel is initialized. Then, Joules are added to the in-memory array. There's your diamond. Next, the boundary edges are established, the compass. And finally, the stopwatch emoji indicates a tick. That's the actual computational cycle where the kernel verifies every single delta and constraint. And remember, if any single part of this topological web fails, the entire commit is completely rejected. But when it succeeds, here is the indisputable proof. A lawful commit with 0 runtime file output, leaving the file system totally untouched. This is the actual verification snapshot directly from the source. The system performed a before and after diff of the entire directory, and the result, exactly 0 lines changed. The C99 demo returned OK1, executed a single lawful commit 1, successfully verified edges 3, and most importantly, runtime file output equals 0. The operation was a massive success, and the system literally left absolutely no footprint behind. As the source material wryly notes, and I think this is so insightful, humans demanded scrolls, then invented printers, meaning this terminal output acts as our unalterable digital scroll. In a way, the developers of FractalFJewel are reacting strongly against the modern tendency to print a physical or digital receipt for every single action a computer ever takes. By forcing all output into this ephemeral, standard output stream of emojis, they've actually recreated the concept of a singular, immutable scroll of truth. Once it scrolls past on your terminal, it's just gone, leaving the underlying system perfectly clean.
Which leaves us with a pretty profound challenge. How can we apply the strict, elegant constraints of FractalFJewel to rethink our own modern software bloat? I mean, this proves that highly complex, strictly verifiable logical operations can happen without endlessly writing to disks, without caching unnecessary data, and without phoning home over a network every 2 seconds. It really asks us to consider, is our current software bloated out of actual necessity or merely out of lazy habit? Thank you so much for joining me on this deep dive into this brilliantly constrained architecture. Keep questioning the defaults, everyone, and keep exploring.